Hello everyone, welcome you are to this new lecture series on control system. The one of the important question that we need to ask that how can you achieve the desired outcome within a system? So, for example, we do have applications like self-driving car, we have drones, and we have efficient building where you can efficiently utilize the energy within a building. So to do all these things, we need control theory. So what is control theory? Actually, control theory is a mathematical framework providing tools for the design of autonomous systems. Now, to understand this, let's consider a block diagram here. So in this block diagram, we can have any system. We do have a car, we do have drone, we do have a building. Okay, so let's suppose this is our system which has some inputs. So there are two inputs shown here. One is known as control inputs that we want to give to the system. For example, in terms of car, we can have steering wheel, brake, accelerator, and unintentional inputs to the system, that is due to wind. We have bumps on the road, we have uphill or downhill, so that is due to the gravity. So these are known as the disturbances to the system. So after that, we have output of this system that can be speed, position or direction of the system. So this is the main idea about the system. Now if we want to design some feed forward control, that our desire is to drive straight with a constant speed. So how we can do that? For that system, we need a controllable input. We need input that provides a particular constant speed. So for that case, we assume that we have a relationship between speed and time here. Okay, so if we look at, as we increase the as time, we can have speed. Okay, now if we want to design feed forward control here, we need a desired pedal fixed non-zero amount so that we can achieve that particular speed. So for that case, we need some mathematical representation about this system. Okay, so to solve this problem, what we do, we assume that, okay, let's see, we want a 30 miles per second as our reference input. So the reference speed that we want is 30 miles per second. So we need some fixed pedal location to achieve this speed. Okay, how we calculate this pedal location, or this pedal where we have to put to get the desired result? So for that case, we need a relation. How we get the relation? We need to know the systems. So for this system, what we know the mathematical model. So how we design mathematical model for this system? We can use first principles. For example, this is a mechanical system that deals with the displacement and motion. So we can use the Newton's second law of motion, that F is equal to ma, to design, to model this mathematically so that we can calculate the relation, okay, between pedal angle and the speed of the car. So, or we do have a data, then we can use system identification technique that fit a model to the data so that we can identify and we know about this model. Okay, so for example, we have this data available, that is speed and pedal angle. So if we look here, there is a relation between speed and pedal angle using this function f. Okay, so this is the, so from here we know that, so to design that, we need a reference speed which is given to us. From this relation, from this graph, we can calculate the pedal angle. If we know the speed, we easily calculate the pedal angle. So that what we do here is, actually we calculate the pedal is f inverse of speed, so which is the desired speed. So from here we get the control desired input. So this is the way we can decide the feed forward control. This control works well unless we have disturbance in the system. For example, if we go uphill or downhill, or there's a bumps in the, so we are unable to solve this because we just do it instead of looking at the dynamics of the system. So this is known as feed forward control. Now to cover up this problem, we have to design feedback control. So how feedback control works, we have the same dynamic system. So from here we have to feedback the measurement. We measure the output and then feedback to the system. So in that case we need an algorithm here which will observe the output and also know the reference. From here you can design the controller. So this is much better. It will based on the dynamics of the system instead of uh, reference input. Now feedback control is powerful but dangerous. Why? Because feed forward changes how we operate a system, because we tell how to change the system, but in case of feedback changes the dynamics of the system, because it's based on this relation, that is x dot equal to f of x, that is based on dynamics. When we change x, it will change the dynamics, so changing the future states of the system based on the current state. So in that case we can change the stability of the system. So this is either way a dangerous thing to design the feedback, but this is also a positive. If we have unstable system, we can stabilize the system by using this phenomena. So a lot of control theory is focused on designing and analyzing feedback controllers, so that we need to do this. And second thing is that feedback control is an expensive control design as compared to feed forward control. But the one of the benefit of feedback control is that we can reject the disturbance to the system. Now there are different types of feedback controller that you can design, and there are a lot of algorithms available. For example, for linear and non-linear, these are the big categories we can divide control into. So in linear we can have PID control, that is proportional, integral and derivative. We can have full state feedback control, that is based on state space. And then we have a non-linear control. One of the type is on-off control. We have sliding mode control. We have Gantt scheduling. Then we have for uncertain systems we have robust control, that based on mu synthesis, active disturbance rejection control. So we do have adaptive control, that based on extreme seeking or model reference adaptive control. We do have optimal control, that is based on linear quadratic regulation, that will solve the optimization problem to calculate the control input. We do have a predictive control, that use the model of the system and predict the optimum control input, that is known as model predictive control. We do have intelligent control. For example, we do have reinforcement learning can be used in intelligent control, or we can have fuzzy control. So these are different algorithms that you can use, but it depends upon the system, in which system you want to use it. So now when we use the feedback, there's one thing we need this state measurement. So for state measurement we need a sensor. So assume that we have a perfect sensor. So this is the algorithm that we need to design. This is the dynamics of the system. Now due to sensors we introduce the noise in the system. Okay, so we have to tackle the noise as well when we want to design the feedback control. Now there are sometimes we want to compare some output with the system reference, but the thing is that output is not available. In that case we need to introduce the sensors, or we need enough sensor to observe all the states. So this is a problem that we can solve using observability, that we can design a state estimation here or observer, so that the unknown states can be measured. So we want to reduce the measurement noise, because if we introduce more sensors, more noise is coming to the system. We manipulate the measurements to estimate the states. Now how we do that? So the answer of this one is the state estimation. So in state estimation, so this is the whole block diagram of the control that we need to know about. So for state estimation we can use Kalman filter, we can use particle filter, we can use running average algorithms to do that. So this is one of the area in control where we can work on the state estimation. Now, when we want to design a controller, we need analysis and we also need simulation and test. So for analysis, simulation and test, we use different techniques. For example, we use border diagram, we use Nyquist diagram, we use Necral chart to do it. So the software that can be used is MATLAB, Simulink or Python to work on these controllers and design. So thank you for this video. See you in the next video.